Okay, welcome. This is the week 9 webinar for the course. So we're starting getting towards the end, but we still have a few more weeks. And let me tell you the plan today. I'll start out with any questions that you have, and throughout, I'm always happy to answer questions if you have them. And then after that, we'll get into the chi-squared distribution. We've had a lot of distributions. We've had the normal distribution, the uniform distribution, the t-distribution, the binomial distribution, and now we're going to get in the chi-squared distribution. And it's going to be used in some pretty important special cases. So we'll have three different tests that involve this chi-squared distribution. The first one will be the chi-squared goodness of fit test. Okay, and then we'll get into the chi-square test for independence. And then finally, we'll get into the chi-square test for homogeneity. So just let you know, these tests, they can address something that we haven't been able to address yet. What kind of study have we not been able to do a hypothesis test for yet? What kind of variable? Any thoughts? See you jumping in. So don't forget, we've done like a hypothesis test for a mean. We've done a hypothesis test for proportion and two means and two proportions. But what we haven't done yet are handling qualitative data that's not just yes, no. So it might be, what's your favorite color? That is not a yes, no question unless you're a physicist and geeky like me. You don't think of those, blue as a number. So that would be a qualitative survey question, or what state were you born in, or country if you weren't born in the United States. So that would be another qualitative survey question. And what we're going to be able to do is we're going to be able to handle hypothesis tests that are about qualitative survey questions. So these are going to be able to handle that, at least some. So that's the plan. Just to let you know, this is week 9, so there's no exam this week. But one thing that you should really start doing is getting ready and working on the project. Yeah, so chi-squared will mostly apply to qualitative data. Okay, there's occasional times when it's quantitative, but you turn it into qualitative, but we'll talk about that. So that's kind of how it's going to handle it. So I figured just a note, chi, chi, is a Greek letter. And this is what it looks like. It's kind of a tall curly X. And then square just means you square it. In terms of mathematically, there's a square going on. The last thing you want to hear me do probably is the mathematics of all this stuff. It's very brutal. But we got calculators that you can let me do all the math for you. But what I do want to show you is what it looks like. So here's an example of a chi-square distribution. Turns out there's degrees of freedom for the chi-square distribution. So this is degrees of freedom 5. And it kind of looks like that. It's a bit skewed right. Okay. It's unimodal. It never has negative values. That's why you don't see negative on the axis. And you would expect that because you're squaring something. You square something, you don't get negative if you square a regular number. And then if you change the degrees of freedom to like a whole bunch more, you'll notice now it's still slightly skewed right, but it becomes more and more normal looking if you have a large degrees of freedom. And if you have really small, it looks like this. Just 1 degree of freedom looks different. Whereas 2 and then 3 looks like that. So anyway, that's the chi-square distribution. And we don't have to do, any of the detailed math on it, but I figure there is a shape of that stuff. Okay. So just a note, because I mentioned the project, one thing I'm hoping you do this week is you post your idea for the project and post your null hypothesis, post your alternative hypothesis, maybe your client, what your sample is going to be, population, and I'll let you know if it'll work. Okay, so again, that's something that you want to do pretty soon so you can get started on that project. Don't wait till the last minute. That's where things go wrong fast. Okay, any questions? Yeah, so the chi-squared is mostly for qualitative data, or if it's quantitative, it turns qualitative, which I'll show you an example of later. Okay, let's do examples. By the way, today will probably be a little shorter than usual because it's one chapter. It's not that bad as long as you don't do the hard math, which you don't. Um, but you should be spending time on the project. So that's the hope. I don't know if you've noticed, but I start this class out a little faster than I end it. I find that helps out. Okay, so here's an example. In California, 40% of residents are Latino, 30% are white, 16% or 34% are white, 16% are Asian or Pacific Islander, and 10% are other races. Okay. Is the distribution of races different for California community college students? Okay, that's kind of interesting. One of the things, if you're, working on the California Community College and trying to make them great, you want to make sure that anybody feels represented. So you want it to kind of look like the rest of California if you can, and not discriminate against one race or something like that. So we'll see if it is. Is it different? Okay, a survey was done. Okay, and when I say a survey was done, I'm making it up. Pretend a survey was done of 300 California community college students. 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. What can be concluded at the 5% level of significance? So, one thing that you should always think about when you do any problems in this class is the survey question. What would the survey question be here? You're going to go to a California community college student. What are you going to ask that person? What's the survey question? Yeah, what is your race? Okay, maybe you can pop in the chat box. What is your race? Tell me. Answer the question. Okay, notice no one said 33. No one said yes or no. So this is something we have not dealt with before. Okay, we have not dealt with a survey question where the answer is quantitative and not yes, no, and we want to do a hypothesis test. So do you see how this is different? And this is, again, this is the chapter 11, which is all about this. So we need to find a hypothesis test that works. And here's what we do. So first thing, we're going to write down the H naught and H1. Okay, I want to let you know, and this is important, when the question is about quantitative or yes, no questions, then you're required to use symbols in your H naught and H1. When your question is a qualitative survey question, then you're required to use words because symbols really don't work for this stuff very well. So instead, H naught, you write H naught colon, that didn't change at all. And then we're going to say the distribution of races at California community colleges is the same as the distribution of races in California. Okay, let me say it one more time. The distribution of races at California community colleges is the same as the distribution of races in California. Why did I scream and yell that word? Distribution? Yep, and if you don't use that word, when I say write down the hypothesis, the null hypothesis and alternative hypothesis for this kind of test, you lose points. Okay? If you don't pay attention to the webinar, you're going to lose points. If you just use AI, it's not going to necessarily use that word. You're going to lose points. Okay, so that's just a note. Okay, and vice versa. If you use that word, you gain points. Okay, even if everything else is wrong. At least I'll give you points for that. Okay, and then H1, very similar. The distribution of races at California community colleges is not the same as the distribution of races in California. Okay, so notice H naught is saying the distributions are the same. H1 is the distributions are not the same. Why is using the word distribution important? Well, a couple reasons. One is it's what this test is all about. Okay. And the other is it helps keep you from using AI. So I have to do that if I can. So it's two reasons. Okay. But even when I teach this face to face and then there's no computer that can do AI that I allow, um, even then I make you say those words or make people say the words. Any questions on looking at the example and then deciding on H naught and H1? Notice there's no symbols here. It's all words other than H naught colon and H1 colon. Any questions? Okay, so the next thing we do is we decide on the test to use. The test we're going to use is called the goodness of fit test, also called the chi-squared goodness of fit test. And it tests to see if distributions are different from each other. When one of the distributions is a known distribution and the other you only have a sample for, but you don't know it. Okay, it's a little bit like a one sample t-test, okay, or one prop t-test, where you know a number and you're comparing it with a number, but now we know a distribution and we're comparing it with that distribution. So here are the steps. So first step is to decide on the test to use, which is good as a fit. The second step is to write down the null and alternative hypotheses. And then the third step is to create a table. And let me show you what the table looks like. So the table is an observed expected table. And what we do is you write down the possible answers. And the answers that we look at is Latino, white, Asian Pacific Islander, and other. Okay, those are the four. Okay. And then we have O and E. O stands for observed. E stands for expected. So O are the observed amount of each of the possible answers. And it's usually just given in a question, or if you do a survey yourself, then that's, you can see it. So for example, it says in California, 40% are Latino, 34% are white, 16% are Asian Pacific Islander, 10% are other races. That's not observed, that's just known. Okay, but then it says a survey was done of 300 California community college students and 125 were Latino. So the 125 is the observed from our survey. So under Latino, O, I'm going to write 125. Any questions on that? So it's important that you know how to create the table. Okay, then we knew 92 were white. So under white, observed 92. Then we were told 33 were Asian or Pacific Islanders. So 33 for O, Asian Pacific Islanders. And then finally, 50 were other races. So the other will be 50. Any questions so far? Okay, so now the next step is we got to find the expected. And the key on the expected, if we know the sample size is 300. And in California, 40% are Latino. So if the distributions are the same, then 40% of all California community college students should be Latino. And if we survey 300 students, if we want to find how many would we expect to be Latino, we just take 40% of 300, which is zero point 0.4 times 300, which is 120. So 120. Oops, 120. Any questions on finding that expected value? Okay, we do the same thing for white. For white, 34% are white. And again, we had 300 surveyed. 34 times 300 is 102, or 34% of 300. 0.34 times 300 is 102. Okay, by the way, you do not have to do it the way I did it. If you don't want to do all the math in your head like I did, you're always allowed to use a calculator. I have fun doing math in my head, so I just do it in my head. Okay. And 16% are Asian Pacific Islanders. So 16 of percent, or 0.16 times 300 is 48. Any questions so far? And then 10% are other. That one you might be able to do in your head. 10% of 300 is, see if you can do that one. That's 30. You don't have to be crazy like me to get that one. Any questions on creating this table, the observed and expected table for goodness of fit? Sometimes that's going to be the hard part because you don't remember how to do it. And you have to remember how to do it. You have to put it in. But, who knows? All right, so we got the table. Okay. Let's use a 5% level of significance. Okay, and then what do you think we're going to do next? Any guess? We need a test statistic and a p-value. Any guess on how we might do that? Yeah, I'm going to use a calculator. And just to let you know, by the way, when I first taught this class, there was no calculator like this to use. So this was really hard. But now you have a calculator, you can just use it. So what calculator number am I going to use? Yeah, 22. This is a goodness fit test. Okay. And the way this has it, it just says observed separated by commas, expected separated by commas. And it has to be in the order at which you write things. So 125, 92. What I'll do, I think the easiest way for me, I'm going to copy. I'm going to paste. And now I got to put commas in to separate them. Comma, comma, comma. Any questions on what I just did? I do the same thing with the expected. Ooh. And I hit copy. And I hit paste. And comma, comma, and comma. Yeah, by the way, I just got the message your internet connection is unstable, so I apologize if we just get shut down. It doesn't happen too often, but once in a while. We don't have any weather outside. I don't know why. Hopefully, we don't have a problem. And hey, calculate. Okay. Yeah, so if my voice is a little weird, then sorry. I might drop my video or something. But if my voice, let me know if you're having trouble hearing me because I'm choppy or something with my voice, because only you know that, and then I'll drop my video if that's true. Okay, so what we have is we have the chi-squared. Here's the graph, remember? We have the p-value. So the chi-squared is a test statistic. That's about 19.209558. I'm just going to copy that. I'll put that here. And the p-value was 0.0002473 about. Any questions so far? Okay, I'm hoping at this point, you know what the next step is based on what we got. Because again, this is hypothesis testing and the steps, it's a step-by-step process. Yeah, we do the conclusion and we look at what we got. Our p-value in particular is 0.000247743. Yeah, so that one is going to be what? If that's the p-value. Here, we didn't even have to like say what the level of significance was. This p-value is so tiny. Yeah, it's definitely less than or equal to 0.05 or less than. So when it's less than 0.05, what do we do? Yeah, we reject the null hypothesis and accept the alternative hypothesis. The word accept or the word reject is not enough, by the way, because you reject the null, accept the alternative. Okay? And then we state our conclusion. Here's the nice thing about the goodness of fit test is I can just copy H1, and that's going to be a big part of the conclusion. So here's what we say. There is strong. I can say the word strong because the p-value is less than 0.01. Remember, that's the necessity for strong evidence. There is strong statistically significant evidence to conclude that. Notice these words, and by the way, if you don't put those words in, I do take off points. There is strong statistically significant evidence. Okay, and if p-value is say 0.03, you wouldn't say strong, you would say there is statistically significant evidence to conclude that the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions? Any questions at all about how this test works? Okay, it's very different than the other in that the other I require symbols for H naught and H1. For this one, it's words. Okay, and I do want you to know that. Okay. So if you're doing something from, chapters 9, 10, 11, I sorry, 9 or 10, it has to be symbols. If you're doing something from 11, it has to be words. Okay. And a lot of that has to do with the fact that this is all about words, right? There's no quantitative anything. Okay. Any questions at all about this idea and how this test works? Okay. Let's do another one. Okay, so does it matter what season a person was born when it comes to the type of car they drive? What do you think? The table shows the season and the car type. So what do you think? Do you think people who are born in winter tend to drive a different kind of car or a different type of car than those who are born in, say, summer? Okay. So you'll hear this a lot. The kind of the example you hear of this kind of stuff is instead of season born, a lot of times people will, and there's people who believe this, but if people think that, hey, if you're a, I'm a Cancer. That's the name. I was born in July, and that's what they call it. Yeah. So if you happen to, know your birth, then you can predict your personality. So that's kind of what this is all about. Okay. And by the way, do you think there's ever been a hypothesis test? I mean, a study, solid study that was done that showed that made a big difference for adults? Okay. And the answer is no. But you can still believe what you want to believe, but it's not statistics. So here's what we got. We got spring, summer, winter, and fall. Those are the seasons. And then we have sedans, SUV, and other kinds of cars. Okay, and this is a table. And just let you know, for example, this number 81, do you know what that means to have that 81 in that spot? I don't see y'all jumping in. That means that of the people that were surveyed, 81 of them were born in the summer and drive a sedan. That's what that 81 means. So it is important you can read a table. And that's what that table means. All right. Is this a good as a fit test? What do you think? Okay. Okay, this is not a goodness of fit test. A goodness of fit test says, is the distribution of something, of a single question at which you observed the same as some expected distribution? Here, there wasn't a single question. There were two survey questions. The first survey question is what season were you born in? The second is what kind of car do you drive? Okay, this is not a goodness of fit test. Okay, so this is going to be a different kind of test. And the test we're going to use is the chi-squared test for independence. Okay, and that's used when we have two survey questions that are both qualitative, and we want to see if they're independent or dependent. Any questions on this? So it's different than a goodness fit test. It's still qualitative. Okay, it turns out we're still going to use chi-squared, but it's not going to be goodness fit. So the next thing we have to do, what do you think the next thing we do once we've decided on the test? Hopefully you'll know. What's the next step? No, not ready for the calculator yet. Good try. Because there's something we haven't done yet. Yeah, we need to state the null hypothesis and the alternative hypothesis. Okay, that's the next step. So let's do that. So H naught, the null hypothesis, is the season a person was born in, and the person's car type are independent. Hopefully you all know I said one word a lot louder than the rest. And H1 is the season a person was born in, and the person's car type are dependent. Okay? If you don't have the word independent for H naught and the word dependent for H1, you lose a lot of points. Got it? Okay, and hopefully everybody's watching this video and paying attention, because if all you do is jump to the end or jump towards the end and you know, just try and find that secret word, then you're going to miss this stuff. And then you lose a lot of points. Any questions at all on H naught and H1? Okay, so now we can use a calculator. Okay, it's not good as a fit. We can't use that. Let's go back to the calculator menu. And what calculator should we use? Yeah, 23. It's test for independence. So I click test for independence. And now it says enter the observed values. Okay, and hit calculate. And the chi-squared test and the p-values will be calculated for you. Leave blank the last rows and columns that don't have data values. Okay, so then we go ahead and we have 73, 81, 76, 78. So 73, 81. 76, 78. And then for the second one, those will be the SUVs, 65, 68, 62, 64. So 65, 68, 62, 64. And for the third one, we have 43, 51, 48, 50. So 43, I believe. Let me double check. Yeah, 43 and 51. And then 48 and 50. Any questions on putting this into the table? Any questions? Just let you know, it turns out whether you look at you look at it this way or you look at it kind of tilted. So if we did 73, 81, 76, and 78 as the first column, so if you switch the columns and rows, it's still going to work. So it's kind of an interesting math that I can't explain too much, but it still works. But I did the way we read it. But just in case you have too many rows that you can fit them as columns, then you could do it that way too for this calculator. If you need to have much more, then you can use a spreadsheet that I made. But this will work for anything that we do in our class. And hit calculate. And there we go. Our chi-squared is 0.48 and a bunch of others. Let's copy it. So our chi-squared, that's our test statistic, is 0.4805559. And the p-value, 0.998067 or so. Then copy that, paste it. Any questions on the test statistic and the p-value? Okay. What do you notice? Notice, by the way, nowhere in here did it give you the level of significance. Do we even need to know the level of significance for this? What do you think? Any thoughts? I don't see y'all jumping in. Notice our p-value is 0.998 or so. That's bigger than any level of significance you would ever use. Okay, so no. Okay. One, and this is standard sometimes in some fields. So you're not given the level of significance, then you use wording. So remember, that's weak statistically significant evidence, just statistically significant evidence, and strong statistically significant evidence, or there is no statistically significant evidence. And this is definitely no. So it depends on the p-value. Okay, so when the p-value is big like this, that's bigger than any alpha. So that means we fail to reject the null hypothesis. So here's what we say. There is statistically insignificant evidence to make a conclusion that the season a person was born in and the person's car type are dependent. Notice all I did was copy and paste the H1 into the end. And that nice thing is it works for these. Any questions? Any questions at all? Always happy to answer. No? Okay, so let's do another example. So do single men and women take the same type of vacation? The table below shows the results of a study. And I should let you know I made this up, but you can imagine doing a study where you do a survey and you ask. Okay. I do want to mention project 2 is not about chi-squared. Don't use anything we talked about today for project 2. Project 2 is about chapter 10, not chapter 11. So that's just a note. So don't even think about doing a chi-squared test in project 2. Okay, so we have a table. Now we have international, out of state, more local. We have male and we have female. Okay, this is different. We have a table, but this is not the same as the test for independence. Because here what we're doing is we're not seeing whether the two survey questions are independent of each other. Now we're saying, if you look at the male answers or the male group, and you look at the female group, do they have the same distribution? Are the distributions the same for male and female for the type of vacation that's taken? Do you see the difference between test for independence and this test? Okay, so just to note, the name of the test we're going to use is the chi-squared test for homogeneity. Have you heard that word before, homogeneity? Not in math, it's just as an English word. You might know it from milk, actually. Do you know that word, homogeneity? Or homogeneous or homogenized? Kind of all from the same root. Yeah, so what it means is it's all mixed up. There's not like levels where this is different than this one. Does that make sense? And that's what test for homogeneity is all about. So that's the test we're going to use, a test for homogeneity. So now what we need to do is we need to write down the null and alternative hypotheses. I think the easiest is to do this. And here's what we have. H naught. The distributions of vacation type are the same for men and women. And H1. The distributions of vacation type are not the same for men and women. Notice now we're looking at two different distributions. Neither of them we know. We don't have an observed and expected. These are both not known. So that's why we can put them together and call them distributions. So if you can have a test for homogeneity, you need to have the word distributions, the plural of distribution, in your H naught and H1. It's not hard if you know what to do. Any questions on that? All right, what's the next step? Yeah, now we go to the calculator. This one won't work. This is a test for independence. That's not what we want. So let's go back to the calculator menu. And what calculator are we going to use? Which calculator? Yeah, calculator 24, because it's a test for homogeneity. I tried to make it, if you remember, if you know what kind of test you're using, this should be really easy throughout the whole calculator. That's what I try to do. Okay, I didn't try and make it tricky or anything. Okay. By the way, we're at 24 out of 26. We're almost done with the class. Next week we'll do 25, and then the week after we do 26, and then we're done. Isn't that cool? So let's hit test for homogeneity. Here, enter the observed values for each of the two samples, A and B, and click calculate, and the chi-square test statistic and the p-value will be calculated for you. Leave blank the last rows that don't have data values. So now we just look at it, and we have the male are 29, 47, 33, 29, 47, 33, 29, 47, 33. And the females were 38, 42, 36. 38, 42, 36. So we go 38, 42, 36. Any questions on entering the values into the calculator? Okay, just let you know, notice here these are columns, whereas in the original question they were rows. The important thing is you understand what's going on. Okay, the male, female, those are the rows, but A and B are columns. And the reason why this is the case is just to make it fit on the screen better. Because sometimes you can have a bunch of numbers for A and a bunch of numbers for B. So rows don't necessarily work as well. And hit calculate. There we go. We have our test statistic, chi-squared, is about 1.4 or so. Let's put that in. And our p-value is about 0.4956. So what do you think? What does this tell us to do at this point? What do you think? What can we do now? Yeah, so now P is 0.4956 or so. That's bigger than any level of significance you'd ever want to use. So we fail to reject. Okay, and then we get to state the conclusion. There is statistically insignificant evidence. Okay, notice a template. This template has not changed in weeks, and it still won't, and you do need to use it. I am not at, I do not grade nicely if you use different wording. Okay, so you do need to use the wording that we do in the webinar. That is important. Okay, if you don't, then what I do is I just guess that you're probably using AI and I'm very mean on points. So make sure you use the wording that we talk about in the webinar. So there is statistically insignificant evidence to conclude that the distributions of vacation type are not the same for men and women. Any questions on this chi-squared test for homogeneity? Okay. This is used a lot, by the way, in research. Okay, this is not the kind of thing that you do at day-to-day life. Okay, that probably won't happen too often, but it is used in research. And when you read published articles, you're going to see a lot of chi-square tests. And one of the things that'll be a requirement for the discussion post assignment this week is you're going to have to find a peer-reviewed published article. And again, you can use the Lake Tahoe Community College Library. You have it open, and then you can see all kinds of published articles. That's the best. That's what I hope for. Any questions so far? All right, let me ask you, what do you think the hardest part of this is going to be? We've seen a lot of steps. What do you think the hardest part? I've been teaching this forever, so I know it's hard. My definition of hard is a lot of people get it wrong. What do you think the hardest part is? For the class, not necessarily real world, but for the class. Hardest part, real world is always collecting your data can be really hard. Remember the exact language used? That's not necessarily the hardest, especially if you take notes during the webinar, then you just have it on paper. You don't have to remember it. It's just sitting there. Do you see that? So take notes, take notes. Write down, write down this, and you can always watch it. If it's too fast for you, you can always go back and watch it on the video. That's not the hardest part, actually. What do you think a lot of people get wrong? Yeah, different methods deciding which test it is. Deciding, are you using homogeneity? Are you using good as fit? Are you using independence? Or maybe it's a, test for two variable differences or, difference between two means or difference between two proportions. So that's where things can go really wrong is if you choose the wrong test, it's going to be a mess. So that's typically the hardest part. Okay, so the best way of getting good at that is practice. Okay, you go to the, chapter assignments, work them out, practice, practice, practice. And that helps a lot. Let's do one more example. Okay, I know we have a lot more time, but I don't think we'll need that much more time. Okay. A study was done asking 100 people how many minutes they spent in the shower last time they took a shower. The mean was found to be 16 minutes, and the standard deviation was 4 minutes. Okay, the table shows results. Is the distribution normal? And I'll show you the table in a little bit, but let me ask you if you can come up with the hypothesis test that will work for this question. What type of test? So what is the name of the test? And by the way, on your exam, you're going to have to state the name of the test. So it is very important that you can do that. So what test are we going to have to use for this particular example? Let's see if you can pop in the chat box what test to use. Okay, you can try independence, but the question is the distribution normal? The test for independence does not tell you about a distribution. Does that make sense? So it can't be a test for independence because the answer for what the conclusion for test for independence is either we don't have, evidence to show they're dependent or they are dependent. But the distribution as normal is never going to be part of a test for independence. Okay, you're saying test for homogeneity, but the problem with test for homogeneity is that's two different groups to see if the two groups have that you don't know their distribution have the same distribution. We don't have two groups. This is one group. It's just 100 people. And we want to see if their distribution is normal. Yeah, that's good as a fit. because we have a distribution we don't know. That's the distribution of shower times. And we have a distribution that we do know, and that's the normal distribution. Okay, so just let you know, this is going to be the goodness of fit test. Okay, so let's suppose here's a table, and there were 20 people observed that spent less than 12 minutes in the shower. There were 73 people observed, or surveyed maybe, that spent between 12 and 20 minutes in the shower. And there were 7 people that spent more than 20 minutes in the shower. Any questions on that? Okay, now we got to find the expected, because that's how goodness of fit works, right? How do we find the expecteds? Any thoughts? Any ideas? I'll give you a chance to think and type it in. So how would I get the expected counts? I got the observed counts, 20, 73, 7, because that was given to us. How do we get the expected counts? Okay, I don't see y'all jumping in. The key is the expected distribution is normal. Okay, so if H naught is correct, it turns out, then the distribution is normal. Well, if the distribution is normal, I'm going to go for the middle one first because that's going to be the easiest. How many would we expect to be between 12 and 20? And notice this is very important. The mean is 16. The standard deviation is 4. 12 is 4 below 16, and 20 is 4 above 16. So how many would we expect to be between one standard deviation above or one standard deviation below? So within one standard deviation, how many would we expect there to be if it was a normal distribution? Any thoughts? See y'all jumping in. Okay. Let me remind you, there's something called the empirical rule. And that said that if you have a normal distribution, do you remember what percent is within one standard deviation of the mean? Do you remember that rule? I know it's been a long time, but we had it. Yeah, 68%. Okay, now here's a really easy question. What's 68% of 100? I hope you don't need a calculator for that. 68. So we would expect to have 68 be between 12 and 20. Any questions on how that worked? If it was a normal distribution, we should have 68. If it was like perfectly normal. Okay, so now the left and right, it's symmetric. If there's 68 in between, then 100 minus 68 is 32. So that means the total outside are 32, but it's symmetric. So how many should be expected or are expected to be less than 12 minutes? Yeah, 16, because again, there's 68 inside, there's 32 outside, and it's symmetric, so 32 divided by 2 is 16. How many would be expected to be greater than 20? This should be really easy. Also 16, because it's symmetric. Left and right should be the same number. Any questions on that? Okay, so the test uses good as a fit, and here is the hypothesis. H naught is the distribution that has to be there of shower time is normal. And H1 is the distribution of shower time is not normal. Okay? And this is really important because that was like if you have a small sample size, for example, you have to assume you have a normal distribution, but sometimes instead of assuming you have a normal distribution, you can run a good as a fit test to find out if you do. Okay, or find out if you don't at least. Any questions on that? So now we go ahead and we need to go back to the calculator. Let's go. And hopefully you all know to use good as a fit. The observed were 20, 73, 7. I can copy and paste the first row, put commas in. And the expected were 16, 68, and 16. And put commas in. And I hit calculate. And there we have it. The test statistic is chi-squared is 6.430147, etc. Copy that in. Pop it in. And the p-value was 0.040152238. Any questions? Any questions? Okay. So if we're just going to do the standard 5% level of significance, then our p-value is 0.04. So what does that tell us? Yeah, reject the null hypothesis. So here's the conclusion. There is statistically significant evidence to conclude that the distribution of shower time is not normal. Okay, so there is statistically significant evidence to conclude that the distribution of shower time is not normal. Okay, by the way, don't even think about putting the word strong here because our p-value is 0.04, and that's not big enough to be strong. It is big enough to have, small enough to be strong. It is small enough to have statistically significant evidence, but not strong statistically significant evidence. Does that make sense? Some people made that mistake on the exam and the discussion post assignment, which I graded. I woke up at 3:30 in the morning, so I had a lot of time to grade. I didn't sleep much last night. I graded. Yeah, the threshold in our class for making strong is 1% or 0.01. Okay, I said that a few times already. Now you'll get it again. Yeah, so weak is 0.1. So in between 5% and 10%, you say weak statistically significant evidence. If it's less than 0.01, you say it's strong statistically significant evidence. If it's between 0.01 and 0.05, you just say there is statistically significant evidence. That's kind of standard. Any questions on that? Okay, sometimes in published papers, If it's strong, you'll see a double star. Whereas if it's weak, where if it's not strong, you'll just see a single star. And weak, you often don't even see a star. So it depends. And again, it really depends on the paper. Any questions at all on the conclusion? Okay, so I want to remind you the hardest part is to decide what test to use. And the best thing to do is practice. Watch my videos, that's good, but you also try doing your own too. Okay. And the assignments, the chapter assignments will help you with that. Okay. So the secret word will be distribution, because for good as a fit, that word has to be there. Distribution. And that's the secret word. So hopefully that makes sense. So that's the secret word for this webinar is distribution. And as I promised, today was going to be a bit shorter. It's only 7:02 right now. But again, I'm always happy to answer questions. That could be about the project. It could be about whatever it is in stats. I do want to mention a few things. One is just a reminder, if you ever need an extension on an assignment, it has to be asked for by the Friday before it's due. If you wait until after, if you wait till Sunday night or Monday, extensions aren't given. Okay, no matter what. So don't wait till the last minute to do your work. Try and get your work done by Friday. And then if something happens, you can ask for an extension, but on Friday. That's the idea. So again, try and get it all done by then. So that is important. Okay. Any questions about anything? Okay, if there's no questions, I think we'll call it. But I'm always happy to answer questions like after I, you know, stop recording if you feel like you'd rather not be public about it. But let me stop the recording.